Welcome to this module on cables and connectors, where we look at all the ways we can connect the various parts and pieces of a modern computer. Some of you may have watched the course I wrote on mobile devices, and the sections on peripheral cabling and video cabling from that course appear again here, but a lot of the other content in this module will be new to you. For example, the clips on network and hard drive cabling, so feel free to focus on the content that you haven't already seen, although refreshing your memory on the other topics might not be the worst idea either. In this clip, we'll take a look at network cables and connectors. One way to group network cables is by their material. Copper cables, for example, come in various forms: coaxial, which we rarely see anymore, and so-called twisted pair cabling, of the shielded and unshielded variety. The other material is fiber optic cables, which can operate in one of two ways: single mode or multi-mode. Well, let's start with copper and work our way to fiber optic. Coaxial or coax cable is built with a central copper core wrapped in an insulating non-conductive material called a dielectric, which in turn is wrapped in a conductive shield to protect from interference. The most common connector for coaxial cable is the threaded Type F connector depicted at left. You may be familiar with this connector from cable television. How is coax used in the IT world? Well, it's often used to connect cable modems and gateways to the cable network, and it's also used, typically in a smaller wire size, for connecting Wi-Fi antennas. In ancient times, when dinosaurs roamed the land, coax was used in Ethernet networks, but that's not something that we see anymore. Here's a picture of the small gauge coax cables that I recently used to add some external Wi-Fi antennas to my small form factor home music server. The tiny round connectors at the lower right snap onto nubs on the Wi-Fi circuit board that connects to the motherboard. Now, the most common type of network cable by far is twisted pair Ethernet with RJ45 connectors, as pictured at left. This cable consists of 8 conductors, and the connector is held in place by a plastic latching tab. You might occasionally see these cables and connectors referred to as 8P8C for 8 position, 8 contact. The RJ in RJ45 is short for registered jack. We'd of course never want to use an unregistered jack, and it's the big brother of the RJ11 jack that has been used in wired phones for several decades now. As for the relevant wiring standards, there are 2, differing in how the wires are color-coded and in the relative position of wires 2 and 3. Probably 95% of the cables in use today use the same standard on both ends, whether it's the A standard or the B standard. Now here's a picture of a garden variety Ethernet cable. They come in all colors and lengths, and the cable specifications are often printed on the cable jacket. Okay, so I mentioned twisted pair Ethernet. What's the point of twisting the wire pairs? You're lucky because we don't have to explore the physics in any detail. All we need to know is that the twists reduce a type of electrical interference called crosstalk, in which the signal in one wire can disturb the signal in a neighboring wire. There's a whole science around the best number of twists per foot, but we can happily ignore that here. What we cannot ignore are the various Ethernet standards, specifically their version numbers expressed as a category and the corresponding speeds and maximum cable lengths. Category 5, or Cat5 for short, can move data at 100 megabits per second over a distance of up to 100 meters. It's pretty much obsolete these days. Cat5e is still quite popular, supporting speeds of between 1 to 5 gigabits per second at up to 100 meters, the exact speed depending on the cable construction and the specific devices being connected. Cat6 is also popular, supporting 5 gigabits per second at 100 meters and up to 10 gigabits per second over the shorter distance of 55 meters. And Cat6a can handle 10 gigabits per second at the full 100 meter length. And now it gets a bit weird. Cat7 and 7a were never formally standardized by the Telecommunications Industry Association, or TIA, but you may still need to remember the speed and distance limits. Cat8 and 8.1 are bona fide ratified standards and can do a very fast 25 gigabits per second over the shorter 30-meter distance. Cat 8.2 uses a different connector and can move a blistering 40 gigabits per second over that same 30 meters. Because Cat 7 and 7a weren't fully ratified by all the relevant standards organizations, and because they use different connectors, they're not very popular in North America. but we do find these cables in Europe. So, what's the story with shielding? Unshielded twisted pair, or UTP cable, shown at left, just has the 8 wires and a jacket, and this physical arrangement is available for categories 5, 5E, 6, and 6A. Shielded twisted pair, or STP, as shown at left now, is available for all the newer category standards and has the benefit of protecting the cable from electromagnetic interference, or EMI, and radio frequency interference, or RFI. So, STP cable, while more expensive to manufacture, is usually a better choice for electrically noisy environments, for example in conduits with a bunch of other electrical cabling. Both UTP and STP can use either solid wires or stranded wires. Solid is more common, but stranded might be better if the cable has to make some sharp twists and turns, or if it just needs to be more flexible. Now, the outer jacket of Ethernet cables also gets a rating. Communications multipurpose, or CM jackets, are made from polyvinyl chloride and emit toxic smoke in a fire situation. Communications multipurpose riser, or CMR jackets, are also PVC, but they have a fire-resistant Teflon coating, so we can use this jacket when running cables between floors in a building, which is where the riser part of the name comes from, risers being the conduits connecting floors. CMP jackets use a different material which produces less smoke in a fire, so these cables are a good choice where network cables need to run through or near heating, ventilating, and air conditioning ducts. Finally, the CMX cable designation, and don't ask me where the X comes from, usually use LLDPE, which can deal with ultraviolet light, water, and temperature extremes, and so it's well suited for outdoor use as well as for being buried underground. Now we turn our attention to fiber optic cable, the kind of cable used with a communications protocol named Fiber Channel, which is popular for connecting computers to storage networks. Optical cables work over extremely long distances compared to copper Ethernet cables. In terms of construction, they're built with cores of glass or plastic that convey the pulses of light, and around that core is a cladding layer that in some cases reflects the light rays down the core. We have 3 types of connectors to know about: straight tip, lucent connector, and subscriber connector, also known as square connector. Here's what they look like. First, the ST connection, which looks exactly like its name would suggest. Here's the LC connector, which is a dual connection. And here's the SC. You can sort of see why its alternate name is square connector. Now, PCs don't normally have optical ports, so we have to add them by means of an expansion card that plugs into the motherboard. A fiber channel expansion card is called an HBA for host bus adapter. This one has 4 LC-type connectors on the mounting plate and connects to the computer via a PCI Express slot. Optical cable can use either single-mode or multi-mode methods. In the single-mode method, a single ray of light travels down the core tube. Many single fibers may be bundled together. The transceivers for single-mode cabling, that is, the circuits we need at each end for converting between light pulses and electrical signals, are more expensive because the cable terminations have to be made very precisely. This mode is often used for longer distances. Multimode, by contrast, sends multiple light beams down the tube, a larger one, and these beams bounce off the reflective cladding layer as they travel. The cable is bigger and costs more, but the transceivers are much less expensive, so that a multimode system often costs less than a single-mode one. Multimode cables are often used in shorter distances. And that's a quick look at network cables and connectors.